Hi and welcome to Unit 1, Topic 1, Video 10, Specialist Maths Curriculum, and we're going to be looking at Pascal's triangle and how it relates to the combinatorics we've been observing already. So you've probably seen Pascal's triangle, I certainly hope you have, and if not, I'll explain it briefly to you now. Basically, Pascal's triangle comes in rows, as you can see there. We have row 0, 1, 2, it starts with a 1, and it's got a diagonal of 1s on each side. And then the in-between numbers are the sum of the numbers above. So 2 is a sum of 1 and 1. And so I can develop the next row. It starts with 1. 1 plus 2 is 3. 2 plus 1 is 3. And 1. 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And 1. 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. So on and so forth. And that's down to row 5. Now, here's the interesting thing, is that these numbers are actually also combinatorics. So this is row 5, and 1 is 5, choose 0, and 5 is 5, choose 1, and 10 is 5, choose 2, 5, choose 3, 5, choose 4, and 5, choose 5. So our combinatorics actually build Pascal's triangle. And so you might have seen this relationship before. It also gives us this nice symmetry right down the middle there. Complete symmetry except for those center number on every second row. We get a complete symmetry, which is what we spoke about in that first video 8, the first combinatorics video. The other interesting thing is that if you sum the rows, the sum is equal to 1. The sum is equal to 2. The sum, that was the worst one, there we go, is equal to 4, is equal to 8, is equal to 16, is equal to 32. The next one is equal to 64. So now we have the powers of 2 in the summation, and that is also what we expect because we're looking at in combinations somebody's chosen or they're not chosen, and you end up with the powers of 2 situation. When it comes to some probability questions, that might be a handy fact to be aware of. So there's some really interesting things that come out of using Pascal's triangle for combinatorics. Now, NCR is therefore the rth term on the nth row. And so the first term on the third row is 3C1. And so that's the link that you need to be aware of that might come in handy. Now here's another thing. We know that each term is in a subsequent row is the sum of the 2 terms above. And it leads to this. So let me show you what I mean. 3C2 and 3C3, when added together, give us 4C3. So in terms of n, if we had 2 terms, let's say we're in the n minus 1th row. So this is row n minus 1. And so we've got n minus 1 C r minus 1 and then n minus 1 C r, and we add those two together. We move into the nth row and we get n C r, which is really cool. And it's also what we've spoken about previously. Now, you may want to skip this part. We're going to go through and do a proof now of the concept we've just been talking about, NCR equals n minus 1 CR minus 1 plus n minus 1 CR. So we're going to start with our left-hand side. Left-hand side is equal to NCR, which is equal to n factorial over r factorial n minus r factorial. And then we're going to work on the right-hand side. So this is going to take a little bit of complex simplification, and we'll need a bit of space for this. So let's go. N minus 1 CR minus 1. And then we need to add to that, hold on. Yep, that's it, n minus 1 CR. And now we're going to put these into factorial form. N minus 1 factorial over r minus 1 factorial, n minus 1 minus r minus 1 factorial, plus n minus 1 factorial over r factorial, n minus 1 minus, n minus 1 minus r factorial. Okay, now we'll carry on. N minus 1 factorial over r minus 1 factorial, and then we'll simplify this bracket. N minus 1 minus r minus 1, well, the minus 1 minus minus 1 will cancel out, leaving us with n minus r factorial only. And then we add to that n minus 1 factorial over r factorial. And again, we're going to simplify the second one, but in this case, there's not a lot we can do except expand the bracket. Now, of course, we're aiming for the same denominator. That's really how we simplify two separate fractions. So the goal here will be to get the same denominator, and to do that, we need to recognize that n minus r minus 1 is 1 less than n minus r. And this is quite tricky, so it's something you really need to consider, and consider strongly. Maybe take some time, maybe even pause the video and think about it. But basically, once I realize that n minus r minus 1 factorial is 1 less, well, I can multiply it by n minus r, top and bottom, and I can increase that factorial. So here's my little recognition. N minus r factorial is equal to n minus r minus 1 factorial times n minus r. But I have to do the same with the top as I've done with the bottom. So on top, I'll get n minus 1 factorial times n minus r. Now the first fraction, I'm going to do the same thing, but this time with r minus 1. And r minus 1 is 1 less than r. So r minus 1 factorial is r less, or a multiple of r less than r factorial. So I just need to multiply top and bottom by r. So I get n minus 1 factorial over r factorial n minus r factorial, but I have to multiply the top by r. Now I've got the same denominator, which is exciting. So I can bring it all into one fraction. I get n minus r factorial times r plus n minus 1 factorial times n minus r. And then it's all over that single denominator now, r factorial n minus r factorial, which happens to be the same denominator as the left-hand side, if you want to have a look at that. So on top, I'm going to simplify. N minus 1 factorial is a common factor, and I have r plus n minus r left over, and the bottom I've got r factorial n minus r factorial. Now on top, r plus n minus r just becomes n. So that's good news. And I've got n minus 1 factorial times n, and then r factorial times n minus r. But n minus 1 factorial times n, well, this is the same principle as we've used earlier. That just becomes n factorial over r factorial n minus r factorial. And of course, this is good now because it's equal to the left-hand side, exactly as we'd hoped. Now, here's another interesting thing for me, anyone. If there are n objects, how many ways can I take m of them, where m is between 0 and n? I.e., how many ways can I choose 0, 1, 2, 3, 4, 5 objects from 5? Well, I can choose 0 objects in one way. I can choose 1 object in 5 ways. I can choose 2 objects in 10, 3 objects in 10, 4 objects in 5, and 5 objects in one way. And if I sum those together, that's 32. And this links directly to row 5. And so this links directly to what I was talking about here with the summations. So it's definitely worth having a look at those and understanding what's going on there. So that's Pascal's triangle and the connection and the idea of Pascal's triangle and how we can relate that to combinations. All the best.